Hello my friends and welcome back to the You Can Do TV channel. The scrap car processing industry plays a crucial role in recycling and sustainability, handling approximately 27 million vehicles globally each year. This process helps recover valuable metals, plastics, and other materials, reducing waste and minimizing environmental impact. The industry not only prevents harmful substances from polluting the environment but also provides raw materials for manufacturing, lowering the demand for new resource extraction. The first step in scrap car processing is collection and transportation. Vehicles reach scrap yards through individual sellers, insurance companies, or government disposal programs. In the US alone, around 12 million vehicles are scrapped annually. Once at the scrapyard, cars are assessed for potential reusable parts and materials before undergoing dismantling. Next, the depollution and dismantling stage ensures the safe removal of hazardous materials. All fluids, including fuel, engine oil, transmission fluid, coolant, and brake fluid, are drained. Each vehicle typically contains 6 to 8 gallons of these substances. Additionally, lead-acid batteries, which contain toxic chemicals, are removed and sent for specialized recycling, along with tires. Globally, approximately 100 million tires are recycled every year. Other hazardous components like airbags and mercury switches are also safely extracted at this stage. After depollution, component salvaging takes place. Parts such as engines, alternators, catalytic converters, and electronic modules are removed for resale in the used auto parts market, which is valued at around $50 billion. These parts help lower repair costs for vehicle owners and reduce the demand for new manufacturing. The next stage is shredding and metal recovery. Once stripped of valuable parts, vehicles are crushed and shredded into smaller pieces. Magnets are used to separate ferrous metals, mainly steel, which accounts for 65 to 75% of a car's weight. Non-ferrous metals like aluminum and copper are sorted using advanced techniques. An average car contains about 2,400 pounds of steel and 300 pounds of aluminum, both of which are recycled and repurposed for new products. Recycled materials play a significant role in reducing energy consumption and emissions. Steel recycling from the auto industry contributes to about 40% of global ferrous scrap metal supply, while aluminum recycling saves 95% of the energy needed to produce new aluminum. However, despite 25% of a car being made of plastic, only 10 to 15% of auto plastics are currently recycled. The global scrap car recycling market is valued at approximately $60 billion, with China, the US, and Europe leading in volume. As the industry evolves, advancements in AI-based sorting, electric vehicle battery recycling, and biodegradable materials are shaping its future. Electric vehicle, EV, battery recycling alone is expected to become a $10 billion market by 2030.
The Arius VZ950, a stationary metal shredder, processes scrap metal through a robust and efficient system designed for high-performance recycling. Two powerful 250 kilowatts electric motors drive the shredding mechanism, enabling the machine to handle demanding materials like car bodies, white goods, engine blocks, and aluminum. The shredder features a revolutionary shaft quick-change system, allowing for rapid adaptation to different materials and reducing downtime. A specially reinforced hopper withstands extreme loads, ensuring durability during continuous operation. Material enters the hopper and is fed into the dual-shaft shredding unit, where it is torn apart by the rotating shafts. The configuration of the shafts and the position of the side combs determine the size and consistency of the output. Processed material then exits via a discharge belt, adjustable to heights of 2,450 mm, 3,450 mm, or 4,670 mm, depending on operational needs. Throughput varies by material. Car bodies achieve 12 to 25 tons per hour, white goods 20 to 40 tons per hour, engine blocks 15 to 30 tons per hour, and aluminum 15 to 30 tons per hour though. These rates depend on equipment setup and material feed optimization. The shredding unit measures 4,500 mm in length, 3,000 mm in width, and up to 4,200 mm in height, with the hopper elevation weighing 23,000 kilograms. A separate control unit, sized at 3,500 mm by 2,300 mm by 2,700 mm and weighing 7,000 kilograms, manages the operation, ensuring easy handling and maintenance throughout the process. Investment casting begins with tooling and pattern making, where a mold, or tool, is crafted to precise customer specifications. Wax is injected into this tool to form a pattern, ensuring accurate dimensions for the final casting. Next, during pattern assembly, individual wax patterns are affixed to a sprue, a tree-like structure enabling multiple parts to be cast simultaneously with molten alloy. The sprue is then repeatedly dipped and coated with ceramic and stucco layers, creating a durable shell. In the dewaxing and firing stage, the mold undergoes flash firing to melt away the waxen sprue, followed by heating to 1800 degrees Fahrenheit and placement on a sandbed. Molten metal, heated 230 degrees Fahrenheit or more, is poured into the hollow mold and cooled. The ceramic shell is broken off in the knockout phase, revealing a tree of solidified parts, which are then separated. Finishing involves removing excess metal, polishing surfaces, and heat-treating the castings for enhanced strength. Finally, rigorous testing and inspection ensure compliance with tolerances and standards before secure packing and shipping. The casting process at Pleisnerguss involves using high-grade steels and nickel-based alloys tailored to specific applications. It employs computer-aided solidification simulations, CNC machining, and rigorous quality controls, including surface, volume, and destructive testing, to ensure top-tier products.
The production of steel coils involves
Rotating rolls reduce the thickness of the material and produce long strips that can be used for manufacturing products such as steel plates.
This process is critical in ensuring the final product.
Each stage requires knowledge and experience to ensure a high. The material is heated in the reheating furnace, rolled in the roughing mill.
The slab is continuously cast and has predefined
Coil
dimensions
box
for the desired final product.
Material to about 1200 degrees centigrade. Two walking beam furnaces feed the material through the oven.
Transport the slab through the oven.
Affects the properties of the
Proper
material.
heating is crucial as
If
it
the
affects the
material is
dissolution
not
of carbides and
sufficiently
nitrates,
heated, incorrect
ensuring
material
uniform material
will
properties.
arise. To the
Insufficient
roughing mill,
heating can
the
lead to
hot
defects
material
in the final
reacts to
product.
the oxygen in the air, and a mill scale consisting
Once
of
heated,
oxide
the slab is
formed
transported
on
to the
surface.
roughing mill.
If the oxide
During this
layer
stage,
remains
the
on
material reacts with
during
oxygen,
rolling,
forming
the
an
layer
oxide
risks
layer
being
known as
rolled
mill
into
scale.
the steel material,
This layer must be
adversely affecting
removed
the
before
surface
rolling to
quality
prevent
of the final
defects.
product.
High-pressure water
material must
jets,
undergo a
160
mill-scale
bar,
cleansing
spray the
before
surface to
rolling.
cleanse it.
In order to cleanse
The slab is
surface,
then rolled
water
in the
is
roughing
sprayed
mill,
at high
where its
pressure,
thickness is reduced from
160 bar.
approximately 22 centimeters to about 3 centimeters through 5 rolling passes. A 4-high
After the
rolling
material
mill,
has
consisting of 2
undergone a
backup
surface
rolls and 2
cleansing,
smaller working
it's
rolls,
sent to
is
the
used.
roughing mill. Here,
Backup
the
rolls
material
provide
is
support,
rolled from its
while working
original
rolls
thickness
directly
of
shape the
22
material.
centimeters down to about
To maintain
3
precise
centimeters.
width control, vertical rolls
This
are
is a very
employed.
significant
After
reduction.
roughing, the material is called a transfer bar. The transfer bar is then wound into a coil box, which serves to save space and equalize temperature across the material. This minimizes temperature differences between the ends of the bar. Upon removal from the coil box, the transfer bar reaches a temperature of around 1150 degrees Celsius. The ends of the bar are trimmed, and further mill scale removal is performed before it enters the finishing mill. The finishing mill consists of 6 4-high rolling stands, where the transfer bar is further reduced to a thickness between 16 mm and 1.8 mm. An uplooper is used to measure and control line speed and strip tension.
Itself.
The first rolling stands focus on profile control, while later stands
In order to
ensure
control the
flatness.
profile and the flatness of the
Maintaining an
strips,
accurate strip
the
profile
working
and
rolls
flatness
are
is essential
horizontally
before
adjustable.
subsequent processing.
The first stand
After
profile
rolling,
and
the
flatness
steel
before
strip
any
undergoes
post-processing
controlled cooling
starts.
to achieve the desired microstructure and mechanical properties. Cooling rates are adjusted based on the required final specifications. The strip is then coiled at temperatures ranging from 150 degrees Celsius to 750 degrees Celsius, depending on material properties. Once coiled and cooled, the steel coil can be either shipped directly to customers or subjected to further processing, such as cold rolling, to achieve additional refinement and mechanical enhancements. The manufacturing process of pipes involves multiple stages to ensure the final product meets stringent quality standards. Below is a detailed overview of each step based on the provided components. Edge milling. This process involves preparing the edges of the pipe material to ensure smooth and precise welding. The edges of the plates or sheets are milled to a specific profile, often V or U-shaped, to facilitate a stronger weld seam. 3-roll machine. The 3-roll machine is used to roll the milled plates or sheets into a cylindrical shape. The 3 rollers exert pressure to bend the material, gradually forming it into the desired pipe diameter. Post-bending. After initial rolling, post-bending ensures the pipe maintains its cylindrical shape and correct dimensions. This may involve further adjustments to perfect the roundness and alignment of the pipe. Tack welding machine. Tack welding is performed to hold the edges of the rolled pipe together temporarily. This involves spot welding at intervals along the seam, providing enough stability for subsequent welding operations. Pipe processing to start. This phase marks the beginning of the main manufacturing sequence. It includes finalizing initial shaping and preparing the pipe for welding. Internal welding. Internal welding secures the seam from the inside of the pipe. This process is crucial for ensuring a strong internal bond, often performed using specialized internal welding machines. External welding machine. Following internal welding, the external welding machine completes the seam by welding from the outside. Visual inspection. Visual inspection is conducted to check for any visible defects or inconsistencies in the weld seam and overall pipe surface. This step is crucial for early detection of potential issues. Pre-washing machine. Before further processing, the pipe undergoes a pre-washing process to remove any contaminants, such as oils, greases, or debris. Expander. The expander is used to ensure the pipe reaches its final specified diameter and roundness. This process involves expanding the pipe uniformly to eliminate any residual ovality or dimensional deviations. Post-washing machine. After expansion, the pipe is washed again to remove any residues from the expansion process, ensuring a clean and ready surface for testing and finishing. Pipe hydrotest machine. The pipe undergoes hydrostatic testing to check for leaks and ensure it can withstand the specified pressure. This involves filling the pipe with water and applying pressure to verify its integrity. Ultrasonic welding detection. Ultrasonic testing is employed to detect any flaws or defects in the weld seam. This non-destructive testing method uses high-frequency sound waves to identify inconsistencies within the weld. X-ray real-time machine. Real-time X-ray inspection provides a detailed internal view of the weld seam and the pipe structure. This method helps identify any hidden defects that ultrasonic testing might miss. End beveling machine. End beveling involves machining the ends of the pipe to prepare them for joining. This process creates a beveled edge that facilitates easier and more secure welding connections in the field. Final inspection. The final inspection is a comprehensive review of the entire pipe, including dimensions, surface finish, and all weld seams. This step ensures that the pipe meets all specified requirements and quality standards before shipment.
The gas cylinder production industry in China has emerged as a vital component of the country's industrial landscape, driven by rapid urbanization, industrialization, and growing demand for energy and medical applications. As of 2023, China is a dominant player in the global gas cylinder market, which was valued at approximately $9.6 billion United States dollars, with the Asia-Pacific region led by China accounting for 35% of the market share. This prominence is fueled by the nation's vast manufacturing capabilities, supportive government policies, and increasing consumption of gases across residential, industrial, and healthcare sectors. China's gas cylinder production caters to a wide range of applications, including liquefied petroleum gas, LPG for cooking, medical oxygen cylinders, and industrial gases like nitrogen and argon. According to industry forecasts, the global gas cylinder market is expected to grow at a compound annual growth rate (CAGR) of 7.9%, reaching $20.1 billion United States dollars by 2033. China's domestic market alone is projected to reach $2.3 billion United States dollars by 2031, expanding at a CAGR of 8%. This growth is underpinned by the country's massive population of 1.4 billion and its shift toward cleaner energy sources, such as LPG and natural gas, as part of environmental initiatives. In terms of production specifics, China manufactures various types of gas cylinders, with steel cylinders dominating the market at 50% of the share in 2023, due to their durability and cost-effectiveness. Composite cylinders, which are lighter and increasingly popular for automotive and medical uses, are also gaining traction. The automotive gas cylinder segment, for instance, was valued at $7.13 billion United States dollars in 2023 and is expected to reach $12.3 billion United States dollars by 2032, reflecting a CAGR of 6.24%. China's output includes Type 1 cylinders, favored for their corrosion resistance, which constitute a significant portion of production, especially for LPG usage in rural households. The industry's scale is supported by major players which dominate related sectors such as natural gas production, alongside specialized manufacturers who are expanding their footprint in China. In 2023, China produced 232.43 billion cubic meters of natural gas, a 5.6% increase from 2022, with a portion of this gas stored and distributed via cylinders. Government policies, such as the 14th Five-Year Plan aiming for natural gas production to exceed 230 billion cubic meters by 2025, bolster this sector. However, challenges like fluctuating raw material costs, iron ore and scrap metal prices spiked in recent years and supply chain strains persist. Despite these hurdles, China's gas cylinder industry remains robust, with exports contributing to its global leadership. By 2030, the market is poised to expand significantly, aligning with trends toward sustainability, such as eco-friendly composite cylinders, and technological advancements like IoT-enabled monitoring, ensuring China's continued dominance in this critical industry. The production of copper anodes at a facility like the Horn smelter involves a meticulous multi-stage process that transforms copper concentrates and recyclable materials into 99.1% pure copper anodes. It begins with receiving over 740,000 tons of copper-bearing concentrates annually, arriving in powder form with 10% to 40% copper content, alongside 100,000 metric tons of recycled materials such as obsolete circuit boards and manufactured copper products. Certified scales weigh transport units before and after unloading to ensure accuracy, followed by sampling to assess metal content. Techniques vary by material type. Concentrates are sampled via pipes at multiple railcar points, while recyclables are captured by automatic samplers and conveyor chutes. Laboratory analysis of these samples, processing over 55,000 annually, confirms precise metal values using advanced methods. Next, materials enter the Naranda reactor. Heated to 200 degrees Celsius, a high-speed slinger projects materials into the vessel, where they liquefy. Oxygen-enriched air is injected, binding sulfur and iron, forming a gas phase of sulfur dioxide above two liquid layers: slag, containing iron, silica and 4% copper, and matte 70% copper. The molten matte transfers to the Noranda converter, operational since 1997, enriching it to 98% copper. Here it becomes white metal 80% copper, further oxidized to remove sulfur, yielding semi-refined copper. This copper proceeds to the desulfurization vessel, where oxidation at 200 degrees Celsius eliminates remaining sulfur traces. Pipe fabrication begins with cutting pipe to length using an automated plasma table, programmed to precise specifications. Joints are prepped and fitted, aligned with mechanical and digital levels for accuracy. Welding follows, adhering to API 1104 standards, utilizing processes like RMD, pulse or spark, with positioners rolling 90 to 95% of welds for efficiency. Certified inspectors and welders review procedures before starting each joint. Root and hot passes are applied to larger joints, followed by final welds. Completed fabrications undergo quality checks to ensure tolerances are met. The molten copper then moves to an anode refining furnace, where natural gas removes residual oxygen, achieving 99.1% purity. Finally, it is cast into solid anodes and cooled with water. These anodes, still containing valuable metals like gold and silver, are transported to a refinery for final processing into 99.9% pure cathodes. Byproducts are managed efficiently. Slag is cooled, crushed, and processed in flotation cells to recover a 40% copper concentrate, returned to the reactor. Sulfur dioxide is captured, converted into 640,000 metric tons of sulfuric acid annually, serving industries like pharmaceuticals and automotive. This streamlined process ensures high-quality copper anodes, while maximizing resource recovery and sustainability. The Davi MAV 3-roll variable axis plate rolling machine efficiently bends thick plates, up to 130 mm 5 inches, into cylindrical shapes. This robust machine completes the process in minutes, leaving minimal flat ends for a precise finish. Featuring motorized rolls and a sturdy frame, it ensures high accuracy and productivity. The tilting rolls allow for precise cone bending, while mechanical and hydraulic symmetry improve tolerances and load distribution. Equipped with the patented servotronic system, roll parallelism is maintained, and a multi-gearbox setup enhances operability and maintenance. This powerful tool delivers reliable, high-quality results for demanding plate bending applications. The rolling process for 10-inch SCH-40 pipes is used in the Jakarta LRT project, ensuring precise bending for structural integrity and seamless installation in railway infrastructure. Mastercam dynamic motion technology enhances machining efficiency, as demonstrated by Cypher_Steiner Precision Style, a company producing an exceptional rim with this system. This technology significantly boosts productivity across various applications. It simplifies cutting hard materials, overcoming their unique challenges with ease. Compatible with both new and old machines, it improves performance universally. Cycle times drop remarkably between 25% and 75% thanks to its material-aware approach, whereon machines decreases due to smoother movements and fewer toolpath reversals, preserving equipment longevity. Tool life extends dramatically, reducing the frequency of changes, increasing part output, and cutting costs. Videos showcasing these 5 key benefits: easier hard material cutting, machine versatility, reduced cycle times, less machine wear, and longer tool life illustrate how this technology transforms manufacturing processes. Companies seeking to elevate productivity can witness its impact in action, delivering precision and efficiency effortlessly. The BW32 wire butt welding device produces strong, consistent welds with high quality. It features automatic control for seamless operation, precise parallel guides for accurate wire alignment, and a robust, reliable design built to last. Easy to operate and maintain, the BW32 ensures efficient welding by securely joining wire ends through a controlled electrical current, melting and fusing them together, making it ideal for various industrial applications. The SMS Maya forging machine operates with precision and power at the Dongbei Special Steel Group's facility in Dalian, China. An 80 to 100 meganewton open die forging press and an SMX 800 radial forging machine, boasting 16 meganewtons per cylinder, shape ingots up to 70 tons. Heated to 250 degrees Celsius, An ingot is moved by crane to the press, where a manipulator positions it. The prestressed tie rod design ensures rigidity as the ingot is stretch forged, upset, and reshaped into squares or octagons. Program-controlled strokes and manipulator movements, synced with forge-based technology, optimize schedules, enhance energy efficiency, and produce high-quality forgings for industries like aerospace and shipbuilding. China's saw blade production industry is a vital component of its manufacturing sector, driven by rapid industrialization and global demand. As of recent estimates, China accounts for a significant share of the global saw blade market, which was valued at $15.68 billion in 2024 and is projected to reach $22.13 billion by 2032, growing at a CAGR of 4.4%. Within this, China's domestic market is expected to hit $5.6 billion by 2033. Fueled by its construction and woodworking industries, the country produces a wide range of saw blades, including circular, diamond, and carbide-tipped varieties, with major manufacturers like Tenyu China Saw MFG Co. Limited and More Top Tools leading the charge. In 2023, the Asia-Pacific region, dominated by China, contributed over 46% to the global market's growth, thanks to an annual output of millions of units. Precise figures suggest over 10 million circular saw blades alone. Export hubs in Shanghai and Jiangsu ship blades worldwide, with competitive pricing averaging $5 per unit for standard models. Government investments in infrastructure alongside a focus on automation have boosted production efficiency, solidifying China's position as a global leader in this industry. The MC650 Nargesa tube and profile bending machine operates with a robust three-roller traction system, essential for bending large hollow tubes and profiles without surface damage. Constructed from welded and machined steel plates, its sturdy frame ensures stability and durability. The machine features tempered flat pinions for secure transmission and F15 for steel shafts, hardened and ground for precision. Electro-hydraulic power drives the rollers, lower ones at 65 mm and the upper at 80 mm in diameter, with a maximum bending capacity of 4-inch 101.6 mm round tubes. Independent adjustment of the lower rollers, controlled electronically with dimension displays, allows tight curves and efficient material use. 9 standard rollers handle various profiles, while optional rollers tackle round tubes. Lateral correcting rollers and straightening rollers enhance accuracy. Operating at 5 RPM, powered by a 3 kW main motor and a 0.75 kW hydraulic unit, it excels in horizontal or vertical positions. Advanced spiral technologies Trulic system simplifies forming perfect screw flights, like those with a 48 inches outer diameter, 48 inches pitch, and 1 1/4 thickness, without requiring prior experience. This innovative approach integrates software and PLC-controlled machinery to ensure consistent, high-quality results every time. The system addresses past challenges where helix accuracy depended heavily on operator skill and imprecise methods. The process begins with the Truffleite software suite. Its troubling module calculates exact dimensions for cutting flat flight blanks, delivering precise graphical outputs exportable as DXF files. Next, the TrueTool module analyzes material properties to determine the optimal tool setup for the job, eliminating guesswork. Together, these tools replace the need for costly specialists by embedding expert-level knowledge into the system. On the hardware side, TrueForm flight forming tools adapt to various flight specifications without requiring custom-shaped tooling. These adjustable tools accommodate the specific parameters of each screw flight, ensuring precision across diverse sizes and complexities. Meanwhile, the TrueSet forming parameters program guides operators through the setup and forming process. This feature accelerates skill development, enabling novices to master helical flight production in just days. The machinery, controlled by PLCs, executes the forming with repeatability, maintaining the helix's size and shape to exact standards. By combining intelligent software, versatile tooling, and automated equipment, the Trulic system delivers efficient, reliable output. It eliminates the variability of traditional methods, making it possible to produce large, thick screw flights like the 48 inches OD by 48P by 1 1/4. Thick example without extensive training or experience, revolutionizing helical screw flight manufacturing. Aluminium alloy wheels are crafted through a permanent mold casting process, where molten aluminium alloy is poured into a reusable steel mold. The alloy, typically a blend of aluminium, silicon, and magnesium, is heated to around 700 degrees Celsius before being gravity-fed or pressure-injected into the mold. The mold's design ensures precise wheel shapes and enhances strength. After cooling and solidifying, the casting is removed, trimmed, and heat-treated to improve durability. Finally, the wheels undergo machining and finishing for a polished look. The PEMA assembly line for thin-walled structures efficiently handles large diameter shells, such as 6 mm thick, 3.6 meters diameter tanks, without cross supports. Hydraulic fit-up units and supporting arms with rollers ensure precise alignment and maintain roundness. Integrated with a column and boom welding system, it streamlines assembly and welding, enhancing productivity for tank and process vessel fabrication. The main engine bed plate renewal process for the vessel Guardian at Navantia Ship Repairs Fee and Ferrell began in May with a coordination meeting to address safety aspects before the ship's arrival. Following gas-free testing, the vessel reached Navantia's facilities, where repair work commenced immediately. The project stemmed from cracks discovered in the main engine plate dry docking, prompting a detailed engineering effort that led to Navantia securing the renewal contract from ConoPhillips in April. The production department swiftly initiated round-the-clock dismantling, removing components like pistons, connecting rods, and cylinder heads for inspection. A custom frame with hydraulic jacks lifted the engine's upper section and crankshaft, enabling the damaged bed plate's removal. The new 60-ton bed plate was then slid into place using Teflon-sheeted skidways, followed by reassembly, alignment, and extensive testing, culminating in successful sea trials after 70 days. The Jugood Heavy-Duty Vertical Machining Center 2210B is designed for precision cutting of large workpieces. It features a rigid boxway structure for stability and accuracy. The machine operates with X, Y, and Z axis travels of 2,200 mm, 1,000 mm, and 900 mm, respectively. A powerful spindle with a speed range of 20 to 6,000 revolutions per minute enables efficient material removal. The bidirectional twin-arm automatic tool changer holds up to 24 tools, optional 32. Cooling systems for the spindle and ball screws enhance performance, with rapid traverse rates of 12 meters per minute and a maximum feed rate of 10 meters per minute. It ensures high-speed machining and superior surface finishes. Crankshaft production varies depending on the size and application of the component. Large crankshafts, typically used in marine, power generation, and heavy-duty industrial engines, undergo a complex manufacturing process to ensure durability and precision. Large crankshafts are forged using a closed-die forging process with a press force of up to 3,500 tons. For crankshafts between 4.5 and 8 meters in length, open-die forging is employed. The forged blanks undergo pre-machining on CNC turning and milling machines with integrated measurement systems. Surface treatments such as induction hardening and shot peening enhance fatigue resistance. Precision grinding ensures tolerances as low as 1,000th of a millimeter. The final inspection process includes classification checks, torsional and bending strength testing, and fatigue analysis before the crankshaft is preserved and packaged for delivery. Small crankshafts, typically found in automotive and high-performance engines, are produced using highly automated methods. Series production lines with robotic loaders ensure efficiency and repeatability. The manufacturing process starts with forging, followed by CNC machining, drilling, and grinding. Heat treatments, including induction, hardening, strengthens critical areas. High-precision measuring systems maintain quality control throughout the process. Both large and small crankshafts are developed through simultaneous engineering to optimize performance, cost, and design. Advanced simulation and testing methods ensure reliability. With high automation and precision engineering, crankshaft manufacturing remains a core component of internal combustion engine production. The production of the reactor plant for the latest nuclear-powered icebreaker, dubbed the Arctic's nuclear heart, is showcased in this video, spanning 2.5 years. The process involves hundreds of manufacturing operations and rigorous quality control at dozens of key stages. Innovations and advanced technical solutions underscore the complexity and precision required to create this vital component. Designed to power the icebreaker through the harshest polar environments with unmatched efficiency and reliability. Turning and milling operations encompass a range of precise machining processes widely used in manufacturing. Longitudinal turning shapes the workpiece along its axis, while milling a square with a keyway cutter creates flat surfaces or key slots. The process relies on 4 coordinate machining, 3 linear movements performed by the tool along the X, Y, and Z axes and 1 rotational movement executed by the workpiece. This combination allows complex geometries to be crafted efficiently without repositioning the material, reducing setup time and enhancing precision. The tool's linear motions handle cutting, shaping, and finishing, while the workpiece's rotation ensures uniform machining across its surface. Aluminum foil production involves passing aluminum through foil mills at speeds up to 1,500 meters per minute, achieving a minimum finishing thickness of 0.005 millimeters. The process includes slitting, where wide rolls are cut into narrower strips, followed by annealing heat treatment of the finished products to enhance flexibility and strength, ensuring the foil meets desired specifications for packaging or other uses. Such integrated machining is typical in modern CNC, computer numerical control systems, where advanced programming dictates the toolpaths and spindle movements. This method suits industries requiring high accuracy, like aerospace or automotive, producing components such as shafts, fittings, or housings. By consolidating multiple operations into one setup, manufacturers achieve consistent tolerances and optimize workflows. The versatility of turning and milling, paired with coordinated tool and workpiece dynamics, underscores its value in creating intricate, reliable parts efficiently. This approach exemplifies precision engineering's role in meeting demanding technical specifications. The Laminator Optima is a roller mill designed for making bricks and other ceramic products. It works by efficiently grinding materials in two stages: primary crushing and fine refining. This high-performance machine, available in models like roller mill, laminoir, or ensures top-quality results for brick production. Built by it's known for its reliability and effectiveness in processing ceramic materials with precision and ease. An automatic high-speed circular cold saw cuts metal precisely. Steel bars, pipes, plates, and aluminum are sliced efficiently using a rotating blade, ideal for various metal cutting needs.
The fully automatic production of round, oval, and rectangular tubes and ducts is a sophisticated process that optimizes efficiency and precision through several key stages. The process begins with a destacking system that loads metal plates up to 2,000 millimeters onto a slide-in table. This system can handle up to 4 blanks at a time, depending on the tube length, ensuring a steady supply of raw material. Double sheet control mechanisms are in place to prevent errors by ensuring only single sheets are processed, maintaining quality and consistency throughout the production. Following destacking and double sheet control, the edges of the sheets are prepared for subsequent operations, and the blanks are fed into the system for further processing. Manifold production, which can involve either a 2-fold or 4-fold process, caters to different design requirements. The sheets then undergo a 2-roll round bending process to achieve the desired shape, forming the basic structure of the tubes. Using a Trumpf laser source, the edges of the bent sheets are welded together with high precision, ensuring strong, clean, and consistent seams. The interlinking of standalone systems, specifically roll forming and welding, creates a seamless production center for tubes through automation. This integration minimizes manual intervention and maximizes efficiency. From sheet to tube, the process involves automatic transfer, where a portal handling system automatically loads and unloads the roll forming and welding station and transports finished welded tubes to optional downstream operations like brushing and calibrating. The automatic destacking and loading eliminate the need for manual intervention, enhancing the overall production efficiency. After welding, seam planishing is performed to smooth out the welded seam, enhancing the tube's structural integrity and aesthetic quality. The tubes are then annealed to relieve internal stresses and improve their mechanical properties, making them more durable and reliable. Calibrating and expanding processes ensure the tubes meet precise dimensional standards and achieve the required diameter. The system is characterized by its flexibility in handling various geometries, diameters, and lengths of tubes. Simultaneous processing of multiple parts ensures a high level of production output. The modular design of the system includes components such as the stacker, multi-roller, flexmaster, and portal handling equipment for tube finishing, allowing easy adaptation to specific production requirements. The combination of the multi-roller and welding system enables the production of both oval and round geometries. The Flexistar line, including the Forstner coil line and Novatec tube finishing, is an advanced production system designed for the efficient manufacture of thin-walled quality tubes. This innovative, flexible production line is known for its continuous throughput and high-quality output, utilizing a combination of roll forming and laser welding technologies. The Flexistar line operates as a compact tube production center, integrating multi-roller and laser welding equipment. One of its standout features is the ability to adjust the diameter of the tubes without changing tooling, allowing for seamless transitions between different tube sizes. This capability is particularly beneficial for applications requiring alternating production of inner and outer tubes, such as insulated chimney tubes or multi-layer bellows. The process begins with the infeed side, where sheets can be fed from stacks or a coil, ensuring a continuous supply of material. The Forstner coil line plays a crucial role here, handling the destacking and infeed of the sheets. Automatic inline quality control systems can be easily integrated into this stage, ensuring that only high-quality material proceeds through the production line. Once the material is fed into the system, it undergoes roll forming, a process that shapes the flat sheets into tubes. This is followed by laser welding, where the edges of the tubes are joined with precision and strength, thanks to the high-quality Trumpf laser source. The welded seam is then planished to ensure a smooth finish, and the tubes may undergo annealing to relieve any stresses induced during forming and welding. After the initial tube formation, the line offers various tube end processing options, including expanding, beading, flipping, and shrinking. These processes are essential for preparing the tubes for their final applications and ensuring they meet specific dimensional and functional requirements. The modular automation of the Flexistar line allows for easy customization and integration of additional processes as needed. This flexibility ensures that the production line can adapt to various manufacturing needs without significant downtime or reconfiguration. The laser welding of hot water tanks made of stainless steel involves a fully automated manufacturing process in a compact system, optimizing both production space and cycle times. By integrating laser technology with proven MSG technology, production efficiency is tripled, allowing 3 times more containers to be produced in the same time frame, within a smaller area, and with less manpower. This advanced process not only reduces the amount of material used but also minimizes the need for reworking, all while delivering higher quality products. This automated system is capable of manufacturing a range of products in the container industry, including fire extinguisher casings, fire extinguishers, boilers, heat exchanger tank casings, pressure vessels, container bodies of barrels, and hot water tanks. The combination of laser welding and MSG technology enhances productivity and quality, making it a highly efficient solution for producing stainless steel hot water tanks and other similar containers. The innovative 4-roll plate bending system XL700 with linear guides is a groundbreaking solution tailored for the wind industry, particularly in the production of monopiles and offshore foundations. This advanced technology guarantees unparalleled precision and efficiency, essential for meeting the high standards of the sector. The system is equipped with a highly advanced 4-roll rolling machine, which includes linear guides that ensure precise operation. It also features a wind tower automation system, complete with a feeding table, top and side supports, and an onboard tack welding clamping system. All these components are controlled by Siemens CNC technology, which optimizes plate handling and achieves a high level of automation, streamlining the production process. The 4-roll plate rolling system boasts exceptional model capacities, with a maximum plate width of 4,200 millimeters, a rolling thickness of up to 180 millimeters, and a pre-bending thickness of 160 millimeters. These capabilities allow manufacturers to handle large and thick plates, essential for constructing robust monopiles and offshore foundations. The system's heavy-duty and rigid structural frame is designed to ensure extreme accuracy in the final rolled cans, a crucial factor in maintaining the integrity and performance of the finished product. A standout feature of the system is its Rolls electronic balancing system, which guarantees maximum precision. Coupled with a state-of-the-art hydraulic system, this setup ensures impeccable repeatability, enabling efficient series production. The high bending force provided by the system allows for exceptional pre-bending of plates, further enhancing the quality of the output. The hydraulic system is designed to deliver high-speed functionality while maintaining optimized power consumption, ensuring both efficiency and sustainability. Additionally, The automatic calibration functions significantly reduce production time, and the optimized automatic bending functions enable the system to meet the tightest tolerances, particularly for cone-shaped products. Highly efficient roughing, semi-finishing, and finishing applications are critical in tool and mold construction, where precision and surface quality are paramount. Collaborating with Tevis and Eschmann, the project Hekalape demonstrated how highly efficient chipping is implemented in tool construction using material 1.2379. The process was comprehensively mapped using the Eudora 7012 linear, achieving excellent dimensional tolerance and supreme surface results from roughing to fine finishing. The Eudora 7012 linear tool milling machine is a cornerstone of this process, offering unparalleled dynamics in both 3-axis and 5-axis simultaneous chipping. Specifically designed for high-performance, heavy-duty machining of high-strength materials, the Eudora 7012 linear features an overhead design that provides a large processing volume while maintaining a compact footprint. Its dimensionally stable and compact design eliminates the need for foundation placement, making it a versatile and efficient choice for tool and mold construction. This milling machine is particularly suited for roughing, semi-finishing, and finishing applications of customary high-strength materials. Its high dynamic features enable efficient machining in 2.5D for processing ruled geometries, cutting contours, pockets, surfaces, drill holes, threads, and spindle operations. In 3D, the Eudora 7012 linear excels in both roughing and high-precision processing, delivering outstanding surface results and dimensional accuracy. A key focus in the development of the Eudora 7012 linear was ensuring excellent quality of motion control and the highest accuracy of the tool center point, TCP. The integration of linear motors in specially designed machine structural elements optimizes control, minimizes contouring errors, and achieves the highest line speeds. This results in superior motion dynamics, especially when handling in constant geometric pathways. The machine's robust, weight-optimized design, coupled with vibration-damping casting materials in suitable structural components, significantly reduces vibrational excitations caused by the milling process and directional changes. This ensures stability and precision during high-performance machining operations. The advantages of the Eudora 7012 linear are numerous. The A95 grinding machine is designed for sickle-shaped and circular knives up to 1,200 millimeters. Operated via user-friendly touch panel, it ensures high grinding precision and repeat accuracy. The machine is adept at both initial serration and reserration, with the ability to pick up the correct starting point in existing serrations. It stores various tooth shapes, which can be easily recalled. A 2D laser measurement unit detects and corrects flatness and outer contour differences, ensuring a consistent grinding pattern. The machine operates with up to 8 servomotor-driven axes, applying precise and repeatable grinding angles between -5 degrees and 35 degrees, with 0.1 degree accuracy. The adjustable grinding pressure is pneumatically applied, minimizing material removal. The A95 also features an automatic deburring and polishing system. A 120-liter coolant unit prevents overheating during grinding. This combination of features ensures production reliability, quality assurance, and minimal scrap rates, maintaining the exact shape of cutting tools throughout their service life.
The casting process at Italpress and Gauss focuses on precision and automation for light alloy production. Italpress specializes in high-pressure hydraulic machines and automatic work cells for die casting. The process involves injecting molten light alloys into molds under high pressure, ensuring intricate shapes and durability. Since many years ago, automation has streamlined production, with innovations like the two-platen machine. Gauss excels in gravity casting automation, utilizing systems to pour molten aluminum into molds via gravity. Standardized devices and coordinated data flow enhance efficiency across their global installations. Forming a hemispherical industrial steel vessel head involves dishing and flanging. In Romania, the first 3,400 mm by 35 mm steel head was crafted using these processes, shaping robust curved components for industrial use. Loudspeaker production at Precision Devices begins with molten aluminum undergoing high-pressure decast injection molding to form a robust chassis. Precision CNC machining shapes metal components, while in-house wound voice coils are crafted. Modular construction and final assembly integrate bespoke parts, ensuring top-tier audio performance. Assembling a Vatic trunnion-mounted ball valve involves securing the body, installing the trunnion and ball, attaching the stem, and fastening the bonnet. Seals and seats are then added, followed by pressure testing to ensure integrity for the DN800 configuration. Google's fastest submarine cable, connecting the US and Japan, stretches across the Pacific. Specialized ships lay the fiber optic line on the seafloor, enabling a blazing 60 terabits per second capacity. High-voltage cables are manufactured using a precise process in a vertical, continuous vulcanization tower to ensure quality. Conductors, often aluminum or copper, are stranded, then insulated with cross-linked polyethylene via triple extrusion. A smooth aluminum sheath is applied, reducing thermal resistance. The cables undergo rigorous testing in high-voltage labs. The forged crankshaft production industry is a vital part of heavy-duty engine manufacturing, producing high-strength components for automotive, marine, and industrial applications. The process begins with steel billets, typically for 2 Cremo 4 or 4340 alloy steel, which are heated to around 200 degrees Celsius, using massive forging presses. Often between 4,000 to 12,800 tons, the billets are shaped into crankshaft forms. Forge rolling operations refine the grain structure before precision machining ensures tolerances within plus or minus 0.01 millimeters. A 2,500-ton hydraulic press trims and calibrates the shape, followed by controlled cooling to relieve stress. Modern facilities use automated warm straightening systems to correct heat treatments like induction hardening, achieve surface hardness up to 58 HRC, enhancing wear resistance. Advanced CNC grinding and superfinishing ensure surface roughness below RA 0.2 micrometers. High-volume manufacturers produce up to 100,000 crankshafts annually, meeting the increasing demand for high-performance engines in commercial and industrial sectors. Crankshaft machining on the Nakamura WT300, a high-rigidity multitasking machine, leverages its advanced two-turret and dual-spindle design for precision and efficiency. The process begins with the crankshaft blank loaded onto the left spindle, powered by a 15/11 of a kilowatt motor, while the right spindle, with identical power, prepares for synchronized operations. Both spindles can deliver up to 30 kilowatts of cutting power when working together, ideal for turning the shaft. The machine's boxway slide configuration, featuring high-frequency hardened and precision ground guideways, ensures stability across all axes. These slides, hand-scraped using the traditional kissage technique, enhance rigidity and accuracy. The upper and lower turrets, each capable of holding up to 24 tools, 48 total, enable simultaneous cutting on both spindles. This setup balances the machining process and reduces cycle times. The turrets, equipped with a 5.5 3.7 kilowatts milling tool motor, excel at high-performance machining even with small tools, while the Y-axis on the upper turret adds flexibility for complex 4-axis operations. Mid-position indexing and multi-tool holders further expand tool capacity, accommodating diverse crankshaft features like journals and pins. Material removal occurs as the turrets execute turning, milling, and drilling tasks, with the opposed spindle design allowing one end of the crankshaft to be machined while the other is finished concurrently. The low center of gravity wide bed structure minimizes vibration, ensuring precision, combining robust motors, advanced NT smarts controls, and traditional craftsmanship. The WT300 delivers exceptional performance for crankshaft production. The NTX 1000 from DMG Mori machines, a titanium shoulder implant through 6-sided turn and mill complete machining. Simultaneous 5-axis machining handles complex geometries using a direct drive motor on the B-axis, offering a 240 rotation range and 100 min-y speed. The X-axis travel extends to 455 mm 17.9 and paired with a Capto C5 tool spindle, reaching speeds of 12,000 min-y, or 20,000 minutes optionally. Precision is ensured by cooling oil circulation in the body to control thermal displacement. A high-rigidity bed and linear motion guide enhance stability, while optional automation features like an in-motion robot and workpiece unloader boost efficiency. China's socket set production industry thrives, with manufacturing GDP reaching RMB 33.55 trillion in 2024. Exports hit 23.51 trillion RMB in 2023, dominating the global market. Merida carbon frames are crafted through a meticulous production process at the Merida R&D Center in Germany. where specialists leverage decades of expertise in composite materials. The process begins with designers and engineers refining every detail, using premium carbon fibers from top suppliers like Toray and Mitsubishi. In the hot melt process, these fibers are impregnated with liquid epoxy resin, ensuring a uniform structure and precise fiber alignment. This creates pre-impregnated material produced in-house with unidirectional and multi-angle options to meet specific needs. Freshness is maintained by cutting and processing prepregs within a week before the resin hardens. Up to 400 individual prepreg pieces form top-tier frames like the Sculptura, each cut to size and hand-draped around poly bladders. These bladders are inflated with high-pressure air in an oven during curing, while positive molds made of EPS foam, silicone, or polyurethane ensure precise dimensions and smooth interiors. Massive steel, negative molds, weighing over 400 kilograms per half, are heated in the curing oven, compressing the fiber layup with pressurized air to expel excess resin and solidify the composite. After curing, the frame is removed, and excess epoxy is cleared via precise CNC treatment, preparing it for surface finishing and quality assurance. In this case, the CNC screw production process with a square edge and thread involves a sophisticated setup using the Depollution Puma 300Y, a high-precision CNC lathe. The machine starts by securing a C45 steel bar, a medium carbon steel known for its strength and meshing. The CAM department programs the lathe to maximize flexibility, defining precise toolpaths for cutting the square-edged profile and threading. The Puma 300Y's multi-axis capabilities allow it to rotate the material while a cutting tool shapes the square edge, followed by a threading operation where a specialized tool carves the helical grooves. The process optimizes tool speed and feed rates to balance efficiency and service life, ensuring durability aligns with operational runtime. This results in a robust custom screw tailored for its intended application. Railway wheel set production involves crafting axles, solid and tired wheels per N, UIC, and SN standards, followed by assembly, tire replacement, disc and gearing wheel fitting, brake disc attachment, bearing box installation, and static balancing. Heat treatment occurs in gas or electric furnaces with fire clay or fiber lining, managed via PC with data logging. The knife production industry is a multi-billion-dollar market, with global cutlery sales reaching $12.5 billion in 2023. High-end knife makers produce 100,000 to 500,000 units annually, while mass manufacturers exceed 10 million. Stainless steel, carbon steel, and Damascus steel are common materials, with heat treatment temperatures ranging from 800 mil centigrados. Precision grinding ensures blade sharpness down to 15 to 25 degrees per side. Japan, Germany, and the US lead in premium knives, while China dominates mass production with over 60% of global output. The PVSL2 is a highly integrated machining solution designed for differential gearbox housing production. Unlike conventional methods that require two separate machines for double-sided machining, the PVSL2 combines two work areas with a central automation zone in a single unit. This configuration enables parallel and turning machining, optimizing production efficiency. Workpieces are fed flexibly from the rear into the automation area, where a pickup loading system ensures seamless handling. The machine also features a storage table, allowing up to 45 minutes of continuous operation without manual intervention. Additionally, automatic part separation eliminates the need for precise placement of raw and finished components. For enhanced productivity, external automation and robot cells can be integrated. An NC liftoff holder is available for brake disc machining, further expanding its application range. The PVSL2 exemplifies Pittler's commitment to innovation, leveraging over 125 years of expertise in turning and milling technology. Power skiving is an advanced gear cutting process that enables highly efficient and precise machining of internal and external gears. Unlike traditional shaping methods, power skiving operates with a continuous synchronized rotation of the tool and workpiece, ensuring faster material removal. The key to this process is the axis cross angle, which allows the tool's cutting edges to progressively engage with the workpiece, effectively peeling away material to form the gear teeth. To enhance efficiency, power skiving can be combined with other machining technologies such as external automation for loading and unloading raw and finished parts. Workpiece surface calibration and gear indexing ensure precise positioning before machining begins. The process consists of several stages, including roughing, where bulk material is removed, and finishing, which refines the gear profile. Deburring eliminates sharp edges and residual material, ensuring high-quality surfaces. Machines like those from the DV's technology group feature rigid structures and optimized control systems to counteract vibrations caused by rapidly changing cutting forces. By integrating multiple tool carriers, complete machining of complex workpieces is possible, reducing errors from multiple clamping and improving overall efficiency, even for small batch production.
The turret CNC machine is built with a cast iron level bed and slide guide, featuring a 12-tool position BMT hydraulic clamping turret. Its compact structure, high rigidity, and high precision, accuracy of 0.01 millimeters, make it an ideal choice for precision machining. The machine offers intelligent operation, ensuring ease of use and reliability, and integrates leading accessories for dependable performance. Its design includes different automatic unclamping and clamping fixtures, enhancing operational efficiency. Equipped with pneumatic components, it caters to various industry applications. The machine supports radial dynamic milling, axial special shape contour milling, and spiral milling hole operations, all with 3-axis linkage, enabling the creation of complex and precise shapes. For green vehicle manufacturing, it handles outside diameter special shape machining and axial end face groove milling. In aerospace applications, it incorporates hydraulic accessories and can perform spindle rigid tapping M6*1, outside diameter grooving, and radial keyway milling. The upright roll forming machine operates through an automated, streamlined process, enabling efficient production. The process begins with the uncoiler, where coils of metal are loaded and unrolled. The material then passes through the leveling section to ensure flatness and remove any inconsistencies. Next, the metal sheet is fed into the machine using servo feeding, which provides precise control over the material's movement. The punching stage follows, where holes or slots are created as required for the final product design. The core of the process is the roll forming stage. Here, the metal sheet is gradually shaped into the desired profile through a series of rollers. Following this, the material is straightened to correct any deformation that may have occurred during roll forming. In the hydraulic cutting stage, the formed metal is cut to the specified length. The process concludes with automatic discharging, where the finished product is offloaded from the machine. This machine can achieve production speeds of up to 20 meters per minute. Complete machining integrates milling, turning, drilling, and grinding, utilizing DMG Mori's advanced technology cycles for exceptional precision. The interpolation turning cycle enhances the machining of complex contours, offering superior flexibility and accuracy. L measuring ensures precise measurements directly within the machine, minimizing errors and enhancing quality control. This holistic approach allows for seamless production processes, reducing the need for multiple setups and transfers between machines. The integration of these processes within a single machine not only increases efficiency but also ensures consistently high-quality output, making it ideal for intricate and high-precision components. The G50 knife grinding and honing machine is a sophisticated tool designed for grinding and polishing straight knives of various types. Its robust, welded machine bed ensures stability and precision during operation. The guideways are either hardened and groundway bands or solid ways, enhancing durability and accuracy. The machine table comes in different configurations: a fixed chuck, place, an electromagnetic rotating chuck, ELT, or electromagnetic double chucks, ELD, each equipped with adjustment and clamping devices to secure the knives firmly in place. The grinding carriage, made from cast iron, features an anti-lift roll system and tapered gib support guiding system for smooth and precise movement. The machine uses a ball screw system for impulse downfeed, controlled by a digital AC servo drive and an NC operator panel for rapid positioning. The grinding motor, equipped with a strong hollow shaft and high-precision bearings, can tilt for both cross and radial grinding, accommodating various grinding tools like ring wheels, segmental heads, diamond, and CBN wheels. A helical toothed rack and pinion system, driven by a digital AC servo drive, controls the traverse drive, allowing variable adjustments. Coolant water is supplied through the hollow motor shaft and from the sides, with various filtration systems ensuring effective cooling. The electric cabinet is installed separately, and all operational data can be customized to meet specific requirements. The Hermle C32U Dynamic is a high-performance 5-axis CNC machining center designed for complex and precise machining tasks. In this configuration, it is used to machine an end mill cutter made of 1.2312 tool steel, which is commonly used in the production industry due to its good machinability and high toughness. The machine operates by rotating the workpiece and the cutting tool along 5 different axes, allowing for intricate and highly accurate cutting paths. This dynamic movement enables the Hermle C32U to perform simultaneous multi-axis machining, ensuring efficient material removal and superior surface finish. The tool changer automatically selects and replaces end mills, drills, and other cutting tools as needed during the machining process. The box beam roll forming machine is an advanced and efficient production line tailored for the precise manufacturing of box beams. The process begins with uncoiling, where raw material is fed into the machine from a coil. The guiding device then ensures the material is correctly aligned, paving the way for the leveling stage. Here, the material is flattened to ensure uniformity and readiness for the subsequent forming process. Next, the roll forming machine takes over, shaping the material into the desired box beam profile through a series of strategically placed rollers. Once the beam achieves the correct profile, it is cut to the required lengths by a cutting device. The cut beams are then subject to transverse movement, facilitating their shift sideways for further processing. If necessary, the turnover stage flips the beams to prepare them for the final boxing stage. In the final boxing machine stage, the beams undergo final boxing and stacking, ready for packaging and transport. Compared with the conventional setup procedure of your machine, our zero-point clamping system significantly reduces setup times, saving you both time and money. This system eliminates the need for workpiece fastening with screws, positioning with T-slot nuts, alignment, and zero-point determination. Even after an interruption in the machining cycle, a restart is possible without re-zeroing. The modular zero-clamp system offers substantial production flexibility, unlike other systems that use cylindrical or conical clearance fits for positioning. The zero-clamp system functions like an HSK tool taper, providing zero backlash and axial phase contact due to the elasticity of the interface. The zero-clamp clamping system is highly sophisticated, using only one type of clamping bolt, which simplifies logistics. The pallet is placed under the open zero-clamp chuck without tilting, while spring elements keep the locking unit open with an air pressure of 6 bars. When the air hose is bled, the zero-clamp positions the workpiece with high holding force and repeatability of 2.5 microns. Conventional systems often face issues with thermal variations causing workpiece displacement. The zero-clamp system avoids this by using clamping cones with radial springs that compensate for thermal dilation, ensuring the pallet zero point remains centered on the turning axis even under high thermal variations. This is essential for machining on rotary tables. The system's simple components guarantee high operational reliability, unaffected by chips. By fastening a single clamping bolt directly to the workpiece, further clamping devices are unnecessary, making machining easier and more economical. Various chuck sizes and designs allow seamless integration into your production environment. Individual base units can be supplied and customized for your machines. For active clamping devices, the clamping table can be easily docked onto an existing energy supply. Zero Clamp is a comprehensive, easy-to-handle modular system. For 5-axis machining, we provide consoles to extend distances to the clamping table and appropriate clamping accessories. Zero Clamp clamping systems offer a tailor-made, efficient, and economic solution for automation in machining. The E50 fully automatic hand knife sharpening machine represents a leap forward in the automation of knife sharpening processes. It is designed to handle a wide variety of hand knives, operating fully autonomously to ensure consistent quality and performance throughout its sharpening cycle. The machine begins by loading knives into its magazine, which can hold up to 48 knives across 2 boxes. Each knife is individually optically detected before the sharpening process commences, allowing the machine to accommodate knives of different shapes and sizes with ease. Prior to sharpening, each knife undergoes precise measurement at a dedicated station. Here, the machine scans and captures the knife's shape, converting this data into CNC instructions. This ensures that the original profile of each knife is faithfully maintained throughout subsequent sharpening cycles. Once measured, a 4-axis operated knife gripping arm takes over, guiding the knife through the various sharpening stages. This includes crucial steps such as deburring and polishing, which are performed quickly and gently to achieve optimal sharpness while preserving the knife's integrity. In terms of productivity, the E50 boasts an impressive output capability of up to 450 hand knives per 8-hour shift. This efficiency significantly enhances production rates compared to traditional manual sharpening methods, requiring only minimal personnel deployment, 1 to 2 hours. Quality assurance is further ensured through optional sharpness testing, where each knife can be evaluated to meet specific sharpness criteria before being returned to service. The machine is equipped with health-supporting technologies such as a serial suction unit and water cooling system.